Welcome to Creative World. In this video, we will solve Chapter 3 exercise problem number 3.9. While solving this problem, we will be using Kirchoff's current law. According to this law, a cumulative current on a node inside an electrical network is always equal to 0. Sum of all entering currents on a node is always equal to sum of all leaving currents from that node. We also will be using Ohm's law. According to this law, voltage across any resistance R is the product of current through it and the value of resistance itself. Now move towards the problem. Exercise problem number 3.9. Find the value of current I0 in given below figure. This is the circuit diagram of given problem. Inside this network we have to find value of current I0 through this 1 kilo ohm branch. So without wasting time, let's proceed towards the solution of the network. This problem can be solved with two different techniques. One is the nodal analysis technique and other one is shortcut to solve this problem. First of all, we will solve this problem using nodal analysis technique. In the end of video, I will solve this problem using shortcut as well. Because in this video series, we are following nodal analysis technique. So first of all, we will prioritize to apply nodal analysis on this network. Later on, we will focus on shortcut technique. That shortcut technique will be focusing on Kirchoff's current law application. So in order to apply nodal analysis on this network, we have to follow some steps. First step includes finding out the maximum number of node equations that can be retrieved from this network. So using this equation, we can calculate that figure. In this equation, n represents the number of nodes that exist in the network. So in this case, there are 4 number of nodes. 4 minus 1 will be equal to 3. So we can retrieve maximum 3 number of node voltage equations from this network. In second step, we have to label all unknown non-reference node voltage. These node voltage are labeled as V1, V2 and V3. This node will be considered as reference or ground node. In third step, we have to assume all unknown branch currents along with their directions. So in this case, these two branch currents are assumed with their respective directions. Now we will apply Kirchoff's current law one by one on these non-reference nodes to find out their respective voltage equations. We will start from here. On this node, two currents are entering, 4 mA and I1, while only one current is leaving, that is 6 mA. Leaving current is taken with negative sign while entering currents are taken with positive sign. We will subtract 4 mA from 6 mA. It will become minus 2 mA because larger value have minus sign along with it. Current I1 is flowing between node voltage V2 and V1. So the value of current I1 will be equal to the potential difference between these two voltages divided by the value of resistance. And the direction of current I1 is from node 2 to node 1, which is indicating that voltage on node 2 is on higher potential than node 1. So potential difference between these two node voltages will be taken as this node voltage V1 will be subtracted from V2. So equation of current I1 will be V2 minus V1 divided by 2 kilo ohm. Now in order to omit all denominator values, we will multiply this equation on both sides with 2 kilo ohm. Product of 2 kilo ohm will cancel out with 2 kilo ohm in denominator. Only V2 minus V1 will left. Here product of 2 kilo ohm and 2 mA will result 4 volt. Place this constant value on the other hand side of equal and rearrange this equation. The equation will become minus V1 plus V2 equal to 4 volt. We cannot further solve this equation, so leave it for now and label it as equation A. It is the first node voltage equation of this network. Now we will apply Kirchoff's current law on this node. On this node, only one current is entering, that is 2 mA, while two currents are leaving, I0 and I1. Both leaving currents are taken with negative sign and entering current is taken with positive sign. Now we have to replace these two currents with their respective equations. Current I1 is equal to V2 minus V1 divided by 2 kilo ohm as we have calculated in previous step, while current I0 is between these two node voltages. and the direction of current is from node 2 to node 3, which is indicating that node 2 voltage is higher than node 3. So potential difference between these two nodes will be taken as V2 minus V3 divided by the value of resistance will be equal to current I0. V2 minus V3 divided by 1 kilo ohm. Now in order to omit all denominator values, we will multiply this equation on both sides with 2 kilo ohm. Product of 2 kilo ohm and 2 milliampere will result 4 volt. Here product of 2 kilo ohm will cancel out with 2 kilo ohm in denominator. Only V2 minus V1 will left. Here product of 2 kilo ohm will cancel out with 1 kilo ohm in denominator. Only 2 will left, and that 2 will multiply with V2 minus V3. Now open these brackets and place this constant value on the other hand side of equal. The equation will become minus V2 plus V1 minus 2V2 plus 2V3 equal to minus 4 volt. Rearrange this equation and add values having same variables together. The equation will become V1 minus 3V2 plus 2V3 equal to minus 4 volt. We cannot further solve this equation, so leave it for now and label it as equation B. It is the second node voltage equation of this network. Now we will apply Kirchoff's current law on this third node. On this node, one current is entering I0 while two currents are leaving 4 milliampere and I2. In next step, we have to replace these two currents with their respective equations. Current I0 is equal to V2 minus V3 divided by 1 kilo ohm, while current I2 will be equal to V3 divided by 2 kilo ohm. Now in order to omit all denominator values, we will multiply this equation with 2 kilo ohm. Product of 2 kilo ohm and 1 kilo ohm in denominator will cancel out with each other. Only 2 will left, and that 2 will be multiplied with V2 minus V3. Here product of 2 kilo ohm and 2 kilo ohm in denominator will cancel out with each other. Only V3 will left. Here product of 2 kilo ohm and 4 milliampere will result 8 volt. Now place this constant value on the other hand side of equal and open these brackets. The equation will become 2V2 minus 2V3 minus V3 equal to 8 volt. Add values having same variables together. The equation will become 2V2 minus 3V3 equal to 8 volt. We cannot further solve this equation, so leave it for now and label it as equation C. Up to this point, we have retrieved 3 node voltage equations from this network. Now we will solve these equations to find out voltage V2 and V3. If we succeed to find out the value of voltage V2 and V3, we will be able to calculate current I0 as well. And it is the required parameter in this scenario. For that purpose, first of all, we will add equation A and C together. The resultant equation will be minus V1 plus 3V2 minus 3V3 equal to 12 volt, and we will label this equation as equation D. Now we will add this resulting equation with equation B. This minus V1 and plus V1 will cancel out with each other. Here also 3V2 and minus 3V2 will cancel out with each other. Minus 3V3 plus 2V3 will be equal to minus V3, and on the other hand side of equal, 12 minus 4 will become 8 volt. Now we will divide on both sides with minus 1 in order to find out the value of voltage V3, that will be equal to minus 8 volt. After calculating the value of voltage V3, we will place this value inside this equation C to find out the value of voltage V2. So in this equation C, V3 is replaced with minus 8 volt. Now open these brackets and multiply minus 8 volt and minus 3 volt together. The equation will become 2V2 plus 24 volt is equal to 8 volt. Place this 24 volt on the other hand side of equal. It will become minus 24 volt. Add these values together. Their resultant will be equal to minus 16 volt. Now in order to find out the value of voltage V2, divide on both sides with 2. V2 will be equal to minus 8 volt. We have found the values of voltage V2 and V3. We are able to find out the value of current I0 using this equation. I0 is equal to the potential difference between these two node voltages divided by the value of resistance. Replace V2 and V3 with their respective values. Open these brackets. This minus outside of the bracket will multiply with minus 8. It will become plus 8. Now the sum of minus 8 volt and plus 8 volt will become 0 volt. 0 divided by 1 kilo ohm will result 0 milliampere. So the value of current I0 from this branch is equal to 0 milliampere. Now we will solve this same scenario using shortcut. We will apply Kirchoff's current law on this node. On this node 6 milliampere current is entering and 2 milliampere current is leaving. The remaining current should leave from this branch in order to satisfy Kirchoff's current law. So remaining 4 milliampere current will be leaving from this branch and the direction of current will be upward. Okay. Again we will apply Kirchoff's current law on this node. On this node 4 milliampere current is entering while 6 milliampere current is leaving. So in order to justify Kirchoff's current law on this node, 2 milliampere current should enter on this node because leaving current is 6 milliampere while entering current is 4 milliampere, and that 2 milliampere will enter from this branch. So I2 will be equal to 2 milliampere and the direction of current will be towards this node. From this branch 2 milliampere current is passing. Now we will apply Kirchoff's current law on this node. On this node 2 milliampere current is entering and 2 milliampere current is leaving. So remaining current is 0. So 0 ampere current will pass from this branch. Same can be satisfied by applying Kirchoff's current law on this node as well. On this node 4 milliampere current is entering while 4 milliampere current is leaving. So in order to justify Kirchoff's current law on this node, no current should enter from this branch, which is indicating that this branch current will be equal to 0. So this was the shortcut of this problem, but we should learn the actual solution of this problem using different network solution techniques. So this was chapter 3 exercise problem number 3.9. Thank you. See you again in next video.